Okay, let's start at the beginning. Nah, screw that. Let's jump to the end. Ooh, transistors. What's the easiest way to go right now from an idea to something that can actually be manufactured as an integrated circuit? Let's find out. Hi, I'm Pat Deegan. I'm doing a course on ASIC design and sharing what I find along the way. I want to take my high-level digital stuff and get physical, i.e. all the way down to producing the files a fab would need to make a real IC. Today's going to be a crash course on starting with some hardware description and making our way to seeing how the transistors would be laid out on the chip, all using open source tools. I'm getting ready to do an interesting little first real design, and I will get into that in an upcoming video, but really to anyone who's done FPGA or even firmware dev, the hardware description should come pretty easily. Anyway, before trying to design anything useful, I want to explore the hardening process itself and identify any snags I hit, stuff that needs special attention, tools we can use, all that. Okay, you've got some working FPGA project and you want to get it spun into a chip. What do we do, really? If all goes super well, you basically have a bit of setup and then one command to run. Ah, look at that. Okay, back up. I'll cover some of the deeper debug in a bit, but let's start simple with something that just works, get set up, make it, and see how we look at the beautiful results. Thanks to OpenLane, getting your environment set up is super easy. Clone the repo, one make command, then a make test, and from then it's Docker magic, so everything is there and works together, and you can make mount to have a shell with all the toolage available. Good. Okay, now let's get a project processed. To have a specific target, some realistic constraints and environment my circuit would be embedded into, I'm building these for inclusion in the next TinyTapeout. TinyTapeout is like a mini version of the course I'm following, and it lets you take part in multi-project wafers. However, the name says it. It's pretty tiny. You get 150 by 170 micrometers, so about 1/10 of a quarter of a square millimeter. Downsides, that isn't much room. And Tapeout so far have had a system where the I/O is shared with all the project and winds up pretty slow. On the upside, that's supposedly still room for 1,000 logic gates or so. It handles connecting my circuit to the outside world, and it's cheap to play. Though possible in manual mode, using the way TinyTapeout works as an example, I tried to make it easy to start by creating a template structure and wrapping a few functions in a Makefile. Links where you're watching this. This will work if you follow along, but if you're going to actually take part in a real TinyTapeout, do follow the directions over there. All this is just to play around. So let's do it. Okay, so I've got my OpenLane set up here. As per the directives, it works because I can do a make mount and then I'm in OpenLane's world. Cool. So now we're going to set up a project. The way we do that is basically a couple of steps. So I'm going to copy the template to designs. You can see there's some existing designs here, and I'm going to call it fret count, like that. I've also got a little project, Verilog. So that's this thing here. I'll cover it in another video, but the point is it's a little module that's set up right for inclusion in this TinyTapeout type framework. So I'm going to copy that over to the designs right in the top there, and then I'm going to move in. So the steps are, let's edit this info YAML thing. So I've got fret count, and fret count, and that's that. In source, I've got these things. Oops, I need to move the fret count into source, actually. Okay, so in source, we've got some extra stuff and the Verilog. So now it's all about making it, and this Makefile here actually has a bunch of nice little stuff to do it. So make GDS should do the trick. I'm going to time it just so that we see how long it really takes. Syn edit. Stuff is happening. Ha! Okay, cool. So if you say flow complete here, then life is grand. It takes about 1.5 minutes. I have other things running, so maybe that's slowed it down a bit, but usually that's just about right. So cool, it seems to have worked out. How can we see what happened? Well, let's make a PNG of our beautiful creation. This also takes a bit. Ah, there we go. Now let's check it out. GDS render.png. Well, look at that. It isn't all that crisp, but we can actually see a few things, including the various inputs and outputs. Now, the PNG, it gives you an idea what's going on. You can see my design is this blob here, and there's a lot of filler or something like that. There's actually a GDS render SVG if you want to take a look with more resolution. Okay, so basically the same image, except that we might be able to read something here. So there you go. Various I/O. You've got 8 in and 8 out, and stuff connected, and da-da-da. Okay, so that gives you an overview, but let's take a better look at this. And one way is to use the awesome K layout. So I've got a make here that will basically load it up with some same defaults and the file that we created, the GDS. So let's have a look at this. This is K layout, and it looks like a big hairy mess. That is because we have a gazillion cell names here and some wiring and a bunch of stuff. Okay, so let's clear things up a bit. So when you open K layout with these, you get the layers named and stuff like that, but you also get a big mess. So let's take this and remove show cell frames. Okay, now these are the layers here. Let's hide everything that's empty. You can see that metal 1 here is the routing. So if I get rid of that, well, it sure looks empty. So what's up? What's up is that we're looking at the cells here, and this is the top module, and it includes a bunch of stuff, but we don't actually see what's inside. So to do that, you can do a plus, or you can just go display increment hierarchy, and there you go. Oh, lots of things. Okay, so you can tell that my design is here and going up and kind of winding around, and there's lots of other things. And if you click on these, you can see down here, this is a decap. It's interesting because the system by default has fillers and stuff, and it has these V-taps and stuff, but the decaps here, these are decoupling capacitors, kind of what you'd expect, but not what you'd expect. They're actually 2 transistors, and what we think of as parasitics, this actually uses, I think it's because the gate, the oxide layer is so small that the distance between the gate is tiny, and it increases the capacitance for the area. So let's go back to our counter here. Now, it's hard to see what's going on, so you can just double click and it'll turn stuff off. Things that we want to turn off are the various decaps, because I don't care, hide. The fill, don't care, hide. And let's see, the taps. All these things are basically connections to the power grid. If you look at the metal, they're going through there. So let's turn those off. So now we're left with just my design. Now you can play and you can look around with this, and you can actually edit things as well. But the point is, here are the metal layers. Interestingly, if you look at that, let's take a spot where we have, so there you go. These are all standard cells. This must be a flop or a clock buffer or something like that, yeah. And if you look, here are the power connections, and they're basically, the cells overlap so that they can make a grid like this where you have all your power coming in. So K-layout is an awesome way to actually look at and play with what your design is like. You can look at, well, I was looking at metal 1, but you've also got metal 2 routed orthogonally here. And then metal 3 is like fatter stuff, and it goes to the pins as well. And metal 4 is some power stuff, I think. Let's see. Yeah, so you've got power and a little bit of routing there too. So that's cool. Okay, so that's K-layout. You can do it to investigate the standard cells. You can do it to, there like that, K-layout trick. If you want to change your view, you can do it the annoying way, or you can just middle click and change wherever you're looking at. So let's go back to the top. There you go. Okay, cool, K-layout. Now this is a nice way to look at the big picture, look at all the stuff, every transistor, but there are things that you don't know that it won't tell you. So for that, we have some extra tools, and these will come in handy when we're debugging. Ooh, so that just scratches the surface, but it's a good start and it's pretty cool. But the truth is that the frequency counter we were playing with there wasn't the first design I tried to squeeze through the OpenLane flow. The first was actually a little RGB mixer with PWM drivers, and no, things in fact did not go super well that time. The processing was just halting with one complaint after another, and while poking around to figure out what the problem was, I got to learn more about the three big players here and how to dig a little deeper. The big players. This is a fat generalization, but to me so far there are three major players involved in understanding what's going on and getting a design ready. Yosys, OpenLane, and the PDK, Sky 130 in this case. Yosys and its pal Symbiosis are most magical mathematical creatures that do things in ways I still don't understand. Yosys' job is to take your high-level description of the behavior and break it all the way down into a net of simple logic gates. OpenLane is the flow manager. It takes a bunch of tools, Yosys, yeah, but also stuff to do placement and timing analysis and uses all those and the PDK to actually create those GDS files the fab needs. It's the orchestrator of the sequence, and you just need to give it a few hints and let her loose. But it can also be used to do design exploration where you try different approaches and compare the results, which is neat and useful. The PDK is where all those cells we were looking at in K-layout come from. It has the cell footprints, but also information for simulations and a bunch more. It's interesting and there's lots to learn from it, but it's both deep and completely bound to the process and the fab that's doing the work. So let's see what the problems were and how I did not solve them, but did get to dig into the details and play with some new instruments. Okay, so now here's a project that didn't work out so well. Here's an RGB mixer. It basically takes a rotary encoder and does PWM stuff and mixes out an RGB LED. So cool. So let's try to make that. Same kind of project, same everything, just doing a make on this particular Verilog. So it goes through its regular stuff and then, bop. Okay, it's unhappy. So what's going on? It tells me, oh no, I'm out of room, it seems. Use higher density or refloor plan with a larger core area. Okay, suggested target density. Now, if you're doing a TinyTapeout thing, you can't play with this, but in our case, I want to see what's going on, so I will play with it. First, we can try and look at what's happening with the system. What are the big bits? So if I use Yosys here, I'm using a local version because it has X dot. So I'm going to read the Verilog in, and what you can do is read that in like that, and then ls. And you can actually kind of navigate. Let's go into LED 0, and you can see that it's got 10 wires and 2 cells, and I can go into the PWM and see what's in there, and pretty cool. So, but this is all very texty. Let's do something else instead. Let's look at the PWM. I'm going to go show colors. This is just a seed 3, say, and since I'm in PWM, that's what it's going to show me. So here's what this looks like. Okay, so you can actually see stuff like it's got a multiplier here. The duty cycle comes in. It does other things. But you've got these proc and everything like that. This is because Yosys hasn't actually processed this yet. So to do that, I can go proc and then show again. And here we go. This is what it really is once it's been processed. So you've got the same inputs, but you can look at the logic and see what's going on. So more interestingly, what are we looking at? The PWM. So this is a logical view, and it makes sense, but it doesn't quite tell us how big this is in real life. And this is the problem here. I was very naive and I just replicated the PWM 3 times and did it real simple, and it takes a lot of space. So once you convert this to actual cells, I'm using the TinyTapeout, remember, so that's a tiny square, it gets pretty big. So what Yosys does is tech map, and then it converts all those things to single bit operations with transistors. So if we look at this, hello. So this is my PWM. Now let's tech map that, optimize that so it's not too heavy, and then show again. Oh yeah. Okay, so what is this? Okay, so this is very big. This is a good way to check your logic and to figure out what's big and what isn't. You can basically go through everything like that. Cool. Now, back to our thing. It told us to change something, and here we go. With a real-life TinyTapeout, you shouldn't change this, but here we're going to see, I want to see what's going on, and there are a couple of variables we can change. FP core util is the utilization of the core that you're going to want, and the target density is what it told us to change. So let's give it what it wanted 54, 56 or something. Let's give it 56 and try again. GDS. Okay, I think we got past that original bump. Oh, another problem. What's going on? So it's unhappy, and it's saying, I kept trying to deal with the congestion, and in my last passes, I didn't get less than 50% off. So we're congested. So what's going on? How can we look at that? And the short version is that OpenRoad has a GUI, and you can check all the stuff if you find the databases. So if you go to runs here, this is our last run 04, ODB. It creates these databases, and you can load them. You can do this manually, but the Makefile actually make show latest DB. We'll find the newest one and load that into OpenRoad in the Docker container. So here we are looking at this thing, and as you can tell, it seems to be pretty packed. So let's see how packed it is. So in this database, there's lots of information, and one of the things is the heat map. So let's look at the routing heat map. Ooh, seems to be pretty hot. So something that you can do is check the heat map congestion here and say, look, I don't want to go from 0 to 100. I want to go just from 90 to 100. Show me that. Oh, 99 to 100. Okay, so we're way too tight. There's no way that this design in its current stage with all these cells is actually going to fit into there. So yosys optimized everything as much as it could. That's not happening. So I still want to see it happening. So let's do something else. Let's try growing the core. I mean, this is something you really can't do with TinyTapeout, but we're just playing. Let's do it. So the die area, the core utilization is one thing that we could play with, but here it's not going to change anything. The die area is another. So let's do it manual style and just say, all right, give me 200 by 200. See if that works. Make GDS. Seems the extra space is going to help us. We made it to DRC, and all right, I think we're flow complete. Okay, let's check out what it looks like this time. Okay, look at that. Now we have something that's bigger and that's completely routed. As you can tell, we've got our inputs and our outputs. We've got all this wiring here. Let's get rid of the wiring for a second and maybe see our cells. Where are our cells? So to do it manually, if you want to check another database, we can just close this. Yes, exit, and go make interactive. And in this case, we can do OpenRoad GUI, go manual style. And then here we get the Go file, OpenDB. Now what it did was it mounted this workspace into work. And the runs, and the last run, and the results, and final, and I think, which one is it? Results, and let's try CTS. Yeah, so here we see the cells. Now, interestingly, let's see, can I highlight the AllNets? Yes. So there you go. It's not the routed. So depending on which one it is, you'll see different stuff. Here we see the cells, but it's not routed yet. And weirdly, it doesn't let you open another DB, which is, kind of weird. Now, the one thing I still don't know how to do is, okay, let's say it's really congested over here. Do I have a congestion map on this? Probably not. Yes, I do. Okay, so the routing congestion. So let's say I find that this spot is really hot. How do I figure out Well, what are these cells? See, the interface actually tells you what it is. Oh, this is a flop. This is an AND gate. Yeah, okay, that's great. But which part of the design is this? But I don't know. Maybe you can tell me how we find that out, or I will tell you as soon as I do. Still, this is a good way to know what's happening, why things are going wrong. You've got different kinds of heat maps that are possible, placement density, power density. It depends on the, let's see, IR drop. It hasn't been populated. Well, okay, so it depends on the database. I don't know exactly what the rule is in terms of what gets into where yet, but I will be updating you on that as soon as possible. Still, with yosys to look at the design and how it's being interpreted and turned into gates, and openroad to be able to look at all these databases. And on top of the databases, I mean, there are a ton of reports and stuff in here about timing, about everything else. Let's please go away. Yes, go away. So if you look at the runs for RPT, there's a lot of reports. So let's see the static timing. So that has stuff about, oh, look at that. I'm all out of slack. Still, yosys, openroad, and all these reports, good enough to really dig deep into what your design is doing and how it's being created and generated into something that can actually be manufactured. Nice. Okay, that's a good start and highlights a few interesting avenues. Oh, for the intrepid few who've made it this far in the video, you're my kind of people, I have some personal news that may be of interest. I'm really getting into this stuff, and a little while back I offered Matt my assistance with the zeroed ASIC course, the one I'm taking, because I find it interesting, but also because I think getting more people into ASICs, using and producing free software and designs no less, is a good thing. Well, it's on. I'm pretty excited that I'm officially on the team helping with random admin type stuff, but as my capacity increases, I hope to contribute on technical sides as well. This won't have any impact on what I share with you, except maybe keeping me more focused and involved, and if I'm lucky, meeting even more interesting folks with interesting ideas. I'll update on that as anything happens. In the meantime, I'm pushing further into the course and the subject. I probably will go deeper in some of the things we saw today, but next thing I'll cover is how I've been producing these digital designs. I find it kind of neat and hope you will too. If there's anything you're particularly curious about, please let me know. Also, install OpenLane, give it a spin, and let me know how that goes. I'll try to post an update soon. Until then, thanks for coming along on the adventure. Cheers.